Can I start?
Yes, please.
Okay, so I'm going to talk about genomic problems involving copy number profiles. So we will cover two problems. One of them is relatively new, as the other has maybe 2 or 3 years of kind of research kind of record. This is a joint work with Manuel Lafond from University of Sherbrooke in Canada, and my student Panjo. So I will spend maybe 2 or 3 minutes quickly going over the background in case some of you do not quite know the background. So basically, in cancer genomics, one of the central problem is to investigate intra-tumor genetic heterogeneity, which is eventually important for cancer prognostics and in some cases explain of drug resistance. I didn't include the reference here on my slide, but in the paper we do have maybe almost like 8 or 9, I believe. So the reason why we use copy number profiles is for some cancers like the HGSOC, the high grade serous ovarian cancer. In the later stage, you would see a lot of rearrangement and duplications in the genome. So because the information change so fast, sometimes daily, if not weekly. So sequencing the genome itself is not that important anymore. So in that case, we typically consider what we call copy number profiles. Okay, so what is that? So basically, given a genome over n segments, and we assume the segments form an ordered set. So G1, G2, Gn, because eventually we will use vectors, so the position is important. So the copy number profile of G is simply an n vector C1, C2, Cn. So each Ci is basically the number of segments of Gi. Okay. As a very quick example, so suppose this is genome G with 8 segments A, B, C, D, E, A, D, E. The corresponding CMP would be 2, 1, 1, 2, 2. So which means I have 2 copies of A's, 1 copy of B, and 1 copy of C, etc. Okay. So well, in general, we need an algorithm to process this CMP data, and so far, we don't really have a lot of positive or good positive results. So motivation of our work was initially from a CPM paper 4 years ago in Israel. It's called copy number transformation. So in this problem, basically we are given 2 CMP, C1 and C2, and you want to use the minimum number of block duplications or and deletions to transform C1 to C2. So I will define what this duplication and deletion on CMPs next. So a duplication on a segment basically means you increase the value of the segments in that the segments in that segment by 1. So for example, I have this segment 2, 2, 1, 2. The duplication basically means increasing the value of each of them, the corresponding segment on the genome by 1. So it becomes 3, 3, 2, 3. Okay. A deletion is well exactly opposite. You basically decrease the values of this sub vector by 1 and at each position. And the only thing you have to be careful is that if value is already 0, you cannot decrease further to negative. So the CNPs must always be composed of non-negative value. So for instance, in this case, you would need 2 duplications and 1 deletion to convert the C1, which is 1, 2, 2, 1, 2, 1, to C2, which is 0, 2, 3, 3, 4, 2. Okay. The first duplication, is like you take 2, 2, 1, 2 and increase that to 3, 3, 2, 3. And second duplication, take this guy, increase it to 4, 3, 4, 2, and then I will perform 1 deletion on this segment or in the subvector 1, 3, 4, it becomes 0, 2, 3, 3, 4, 2. Okay. So an optimal, though a complex linear time dynamic programming algorithm was presented 4 years ago. So our motivation was that this model on applying this duplication and deletion directly on CNPs sometimes might not be exact or accurate if the evolution depth is large. So here is an example. I started with this genome A, B, C, D, E, F, and the corresponding CNP is 6, 1, right? So then I will duplicate this segment on genome B, C, D, E, and correspondingly you get the CNP 1, 2, 2, 2, 1, right? So over here, if I perform 1 more duplication on DEB, you would increase the corresponding values to B, D, and E, but then you will leave C alone. So in other words, in this case, there's no way you can take this CNP and convert it to the last one with 1 duplication on the CNP. So so what we proposed was one of the first problem we studied was exactly based on what I just covered. At an ACM BCB 18, we proposed the following problem called MCNG. So so you are given a genome G and a copy number profile C, and you want to use a minimum number of duplications and deletions on G, not on the profile, to generate some genome G prime, such that the CNP of G prime is equal to the target copy number profile. So so this problem is real and seems to be very hard for the last 2 to 3 years, and no theoretical result was known for the problem itself. 2 years ago, we basically studied some special case. For example, if the duplications must be tandem, then we obtain some hardness result, and also we obtain some greedy heuristic method with some implementation. Okay. So in this talk or in this paper, we actually, unfortunately, we show that the problem first does not admit any constant factor approximation unless P equals to NP, and also the problem is W1 hard when parameterized by the solution size. Okay. For the second problem, this one is brand new. So we are given 2 copy number profiles, C1 and C2. So we want to compute 2 strings, S1, S2, such that the corresponding CNPs of S1 and S2 are C1 and C2 respectively. And of course, in this case, you want the distance between the 2 computed strings to be small. In our case, minimum. So we show that if the distance is the string breakpoint distance, then the problem is polynomially solvable. And I will leave quite a few open problems at the end, because initially we tried to really look at the tandem duplication distance, but we couldn't make much progress. For duplications on genomes or on sequence, so I will define very quickly. So basically, you select a segment AI to AJ and put this segment before AK or after AK. In the former case, K must be less than or equal to I. In the latter case, K is greater than or equal to J. If K is equal to I or J, then the duplication is random. Okay. Deletion, well, you just take a segment and remove it. Like for example, you take the segment 3AB in red and remove it, you get 1, 2. So this is a pretty standard kind of definitions. So now let's look at some. So maybe I will skip this example. So this is again the summary of results. So I'm going to basically skip the second one, maybe just with one slide, give you the generic idea for W1 hardness proof. For the first one, the negative result, I'll give some details, but not all of them. So I will give most of the details for the positive result. Hopefully I have about 10 minutes, so should be enough. So for the first hardness reduction, we will reduce something called T set cover to MCNG. So this is a special case of set cover where each set contains at the most T elements. In our case, we consider T to be a large, possibly large kind of constant. Okay. The reason why we do that is because Ruka and Trevisan proved about 20 years ago this result on set cover. This is less known, because usually when we talk about set cover, we talk about the generic case. In this case, for T set cover, Ruka showed that it cannot be approximated with, in fact, log T minus C log T for some constant. Okay. Unless P equals to MP. Lastly, a solution for set cover is called an exact cover if the sets, the subsets in the solution for set cover are all disjoint. Okay. So we will make use of this result by Ruka as follows. We showed a slightly more generic kind of lemma so that it works not only for MCNG but might be on something else. So this lemma says the following. So if an instance S of T set cover can be reduced to an instance GS of some minimization problem B with the following properties, then P does not admit a constant factor approximation. So first of all, any exact cover of S of size K can be transformed into a solution of size K for GS for the problem B. And the second, the solution for size, of size K for GS, for problem B can actually be transformed back into a solution for the T, set cover. Okay. So this is the generic kind of lemma. So the proof, maybe I don't really have to go into detail. Roughly goes as follows. So you assume that B has a factor little b approximation, and this little b is less than log T minus C times log T. So apparently in this case, you can select T large enough as a constant satisfying this condition. So the actual reduction is through a very simple transformation. You take the T set cover for each set with at most T elements. Remember, T is a constant. So you enumerate all possible subsets you have in another kind of instance. So in that case, if this T set cover can be reduced to B, and this middle problem where you enumerate in all those subsets of a given set, it would give you an exact set cover of size k. Okay. And so basically, in summary, so I will skip the other direction. So basically, we show that S has a set cover of size k if and only if B has a solution of size k as well. So therefore, the inapproximability result immediately follows. After that, we just need to reduce T set cover to this MCNG. So what we do is as follows. So I will just use this example. So this is a universe with 12 elements. I have 6 sets, S1, S2, S6. In our reduction, we will encode S1, the set, using the elements like 1, 2, 3. So this is very much the reduction. So the genome is composed of Q1, S1, Q2, S2. Each of this set Si is encoded in using the string. Okay. For the CNP, each of this Qi, which is a separator, so we will make sure that they only appear once. For the remaining elements, I will take CNP UI as FUI minus 1. So FUI is a number of sets containing UI. Okay. So for example, with respect to this instance, so this is our sequence, a computer sequence for G. The solution, of course, is simply to delete the 2 sets that does not form or does not belong to the solution for set cover. So you can easily see if we restrict that only deletions are allowed. Apparently this reduction satisfies the 2 conditions in the lemma we just showed. But what is slightly more tricky is that this is also the case when duplications are allowed, arbitrary duplications are allowed. But as a proof, I will not have time to discuss that. It's on page 7. Okay. So this is the first hardness result. For the second one, so MCNG parameterized by the solution size k is W1 hard. So we cannot use the same, or the previous reduction from T set cover because T set cover is fixed parameter tractable. So in fact, we reduce a new version for set cover, which we call set cover with exact cover or set cover EC for short. To this MCNG problem. It has a property that any set cover of size at most k is also an exact cover. So for showing this problem, set cover EC to be W1 hard, we actually reduce the multicolored clique problem to this problem. After that, the reduction are very much the same, following the previous reduction. So let me spend maybe 4 or 5 minutes for the last problem. So in this case, we are given C1, C2. You want to compare compute 2 strings S1, S2, such that the CMP of S1 is C1, CMP of S2 is C2, and we want to minimize the distance between S1 and S2. So distance, as I put earlier, so is pretty general. It could be tandem duplication distance or reversal plus duplication plus deletion distance. So here we consider the string breakpoint distance, and naturally the 2 CMP C1 and C2 they must be different. So otherwise, if they are the same, and of course the solution is trivial, right? So I will probably I don't have to redefine breakpoints and adjacencies. But anyway, let's do that. So basically, given two sequence A and B, you take any two substring in A, like AI plus 1. It forms a match with BJ plus 1 if the two sets AI plus 1 BJ plus 1 are equal. So in graph theory, so there's an edge between this two substrings, okay, in the bipartite graph. So if we compute a maximum matching in this graph in H, then to match the two substrings form an adjacency, and the unmatched ones form breakpoints. So this is a very quick example. So we have three matched pairs in CB with BC, and let's see, DC with CD, and CB with BC. Okay, so the set of adjacencies BC, BC, and CD, and the remaining ones are breakpoints. So the breakpoint distance between A and B is simply the summation of this the size of these two sets, which is 6. And you can easily see the number of adjacencies and breakpoints, they are complementary to each other. It's basically the length of A plus B minus 2 times the number of adjacencies minus 2 is breakpoint distance. So for now, we will form maybe follow more on the adjacencies. Another thing to note is that even for a string breakpoint distance, even if there's no breakpoint between A and B, that doesn't mean A equals to B or B is reversal. And this is an example. Between A and B, there's no breakpoint, but they are different, even if you reverse one of them. Anyway, so so now we will try to design this algorithm to maximize adjacencies between S1 and so finally, given an n vector, I will use SU to denote the multi-set of letters corresponding to U. Like if sigma is A, B, C, D, E, so U is a vector. So SU basically is the set of 3 A's, 2 B's, and 1 C and 1 E. So okay, so I'm almost done. And little s, basically represents one of the strings formed by this set. And apparently, this little SU is not unique. And in our algorithm, we will make use of this property. So lastly, so given integer vectors U and W, so if each component Wi is less than or equal to Ui, then we say W is a subvector of U, also denoted as W less than or equal to U. And consequently, we can define maximum common subvector. So basically, oops. You are given U and a V, and for each component you take the minimum. So 3, 2, you take 2, 2, 1, you take 1, etc. So this is the maximum common subvector. So I will spend maybe 30 seconds to go over this algorithm, and that's very much it. So we basically run this algorithm directly with this example. So C1 is 22241, and C2 is 44111. And sigma, of course, is ABCD, is ordered. You first compute the maximum common subvector V, which is 22111. So then I take this multiset SV, which is AA, BB, CDE, and similarly I compute SC1, SC2. There's a set of letters in corresponding to C1 and C2 respectively. So X is the symmetric difference of SC1. Well, just the difference SC1 minus SC2, which is C DDD, and the Y is SC2 minus SC1, which is AAB. Okay. So if the important thing here is that the elements in X, Y could give us one additional adjacency. If this is y, for the next two steps, we needed to find the xy. So in this case, xy, they are not equal, and not only that, they must be in this multiset SV, and exactly one of them is in X as the other is in Y. So in our case, we take little x as one of the D in this set X, and Y as A in set Y. Okay. So if we cannot find this XY, and there's nothing you can do, just very much form S1, S2 by taking an arbitrary string formed by SV, right? And then add the remaining ones in X and Y arbitrarily at the two ends. But here we could add one more adjacency. This is an example here. So I take compute little SV, which starts with X or D and ends with Y. So it's a DA. And the tricky part is that because X contains D, right? So I can put the D at the end to form this adjacency AD, and which can be matched with this AD here. So Y contains little a, right? So I put A at the front of D. So therefore, to create one additional adjacency. And for the remaining ones, I mean, you just put them arbitrarily at the two ends without breaking the existing adjacency. We showed that if C1, C2 are polynomially bounded, in other words, if you sum their corresponding components, if it's a polynomial, then the number of common adjacencies generated by this algorithm is either n star or n star minus 1, where n star is the sum of VIs, where VI is a component of the maximum common subvector. So as I already mentioned, whether the problem, whether the number of common adjacencies is n star or n star minus 1 is based on whether this xy can be found. Finally, if we simply want this number n star or n star minus 1, then we can withdraw this polynomially bounded condition. Okay? Because otherwise, if you have to construct S1, S2 explicitly, and if this condition is not satisfied, so certainly the length could be exponential. Okay, last slide. Open problems. So there are still quite some problems left. For even for MCNG, if G is a permutation, we don't know whether the problem is NP. For this CNPC, the new problem, we are really interested to know whether the problem is solvable with somehow kind of dynamic distance, like tandem duplication distance. So here dynamic is hand waving. Intuitively basically means if you change the distance like with one more tandem duplication, the string changing completely. And last thing is that the results produced by our algorithm using this static breakpoint distance is certainly not that realistic in for real data sets. So in any case, there's a lot of things to be done. I think I will have to close now.
Okay, so thank you. We are a bit behind time, so if there are any questions, I think it would be better to take them at the